Hello, I'm Michelle Taylor, Editor-in-Chief of Laboratory Equipment. Welcome, and thank you for joining us for the importance of correctly controlled qPCR. Today's webinar is sponsored by Cole-Parmer and presented by Laboratory Equipment. Before we begin, I'd like to quickly explain how you can get involved with this webinar. A question and answer session will follow our final presenter. At any point during the webinar, you can type a question into the panel through the presentation console. The speakers will answer as many questions as time permits. Today, you will hear from two speakers. First, you will hear from Dr. Andrew Birney, Life Sciences Product Manager at Cole-Parmer. Andrew was a researcher at Glasgow University for a number of years and studied nematoid enzymes with relation to collagen modification before moving to more commercial roles within the biotech industry. You will also hear from Dr. Stephen Bustin, Professor of Molecular Medicine at Anglia Ruskin University in England. He is a world-renowned expert on quantitative PCR, and his research focuses on translating molecular techniques into practical, robust, and reliable tools for clinical and diagnostic use. Professor Bustin's research interests include identifying prognostic biomarkers for colorectal cancer and, more recently, developing novel approaches to the early diagnosis of fungal and bacterial pathogens. And now, Andrew is going to kick off our webinar.
Okay, thank you, Michelle. So today we're going to talk about the importance of correctly controlled PCR. I'm the Life Sciences Product Manager, as Michelle explained, and I'm going to cover a little bit about the system and its impacts on performing correct PCR or qPCR in an efficient and correct manner. Stephen, who's been an exponent and a user of this system for a number of years, is going to give some background to that and show some absolutely lovely data that we can go through. And like Michelle said, any questions at any point, just submit those and we'll cover them towards the end. So what we're going to talk about, or what I'm going to give a bit of a nod to start with, is the history of this unit, because it's always a good place to start, is right at the beginning of our story. Then I'll give us a short system overview before passing over to Stephen, and Stephen can get into some more detail about qPCR and how you can make it better and behave the way you want it to. And then at the end, we'll have time for some questions as well. So, as my mother always tells me, it's a good place to start is the beginning. So if we go back to the very foundings of this unit, the unit itself was developed by a company called Helixis. Helixis was a spin-out, for those that are aware of a company called Corbett Research. Corbett was purchased by QIAGEN, and at that point some of the people splintered off, set up a company called Helixis, and they developed a small unit called the Pixel. At that time, I was involved with this unit as I was a sales guy in the UK, and I was distributing for Helixis. Unbeknownst to me, though, Illumina had Helixis on their radar. So Illumina paid $105 million to purchase outright Helixis, and with that, the Pixel. They'd done that because they recognised the importance, or the impact rather, that the box, the Pixel as it was known then, could give to downstream applications, so its accuracy and its speed, and the importance that would have in qPCR outcomes. So Illumina took on that unit, but Illumina got to a point towards the end of October 2013 when they kind of had a bit of a redress and went back to what they know best, which is sequencing. And it was purely because the Eco, as it was known then, was taking up a lot of floor space, as it was told, in their production. So they moved that out and focused back on sequencing. But at that point, Bibi Scientific, one of the largest independent distributors and manufacturers of scientific equipment in the UK, got involved with that. They had just set up this new brand called PCRmax, which was established in September 2013, and we took over the qPCR platform that Illumina had put on the shelf. We relaunched the unit in October of 2014, and it was then called the Eco 48. Since then, been continued on and growing on the foundations that Illumina had put in place and maintaining the quality set that the unit had already defined in the market. So as the system stands in very broad strokes, the unit itself, maybe some of you have already guessed or are familiar with it, is a 48 well unit. But the format isn't like a 0.2 mil tube. The format is actually like a 384 well plate. So it's basically 1/8 of a 384 well plate. So it's the same spacing, it's the same well centres, so multi-channel pipettes will work. And it's a very familiar sort of format for people in the lab. The unit is a 4-colour multiplex system, and absolutely every cycle the unit acquires data from all 4 of those colour sets. So basically when you come to set up your experiment, you can't set it up wrongly, and that you can't use the wrong filter slide or the wrong excitation source. The unit just acquires across the whole plate all 4 colours at all time. So it's really nice for when you're setting up your PCR run. You don't need to pre-configure the software. You just put it in, tell it to go, and then off it will go, and it will acquire all 4 channels every cycle. Read time for the unit is actually 6 seconds for those that are interested, and that's for all 4 colours. I've written here application orientated. That's entirely true. This unit, when you get it, it has all of the feature sets already into it. There's no upgrades or anything like that to this unit. Everything's pre-configured into it. And I've just written there HRM, which is a little kind of badge of honour that this system will wear just based on its thermal performance. But 2 functions that really lend this system to correctly controlling qPCR. One of those is high speed, and Stephen's going to allude to some fantastic data that he does, or fantastic results that he's generated, in his own lab, which have been conferred by the uniformity of the system, or it gives access to run qPCR at incredible speeds, basically. And it's a very small system. It's about a cubic foot, or 30 centimetres squared. So there are basically 2 components to any qPCR system, and I'm going to talk briefly about both. I won't labour too long about it because it would really be more interesting to see the impact of these and how it's exploited in correctly controlling PCR. But you have 2 systems here, an optical unit and a thermal unit, basically. Each of which have to be of a high quality, certainly in my opinion, and certainly in data sets that would back that up, so that you can basically make the most of your experiment. If you've got a very good optical system overlying a slightly less good thermal unit, what you'll acquire is excellently acquired, poorly generated data. And vice versa is also true as well. So really, to get a good qPCR system which you can use to impact your results positively or impact your data sets positively, you need to have a good one of each of these. And I'm happy to say that in this platform, they are good for both of them. What you have is basically in this unit, and we won't go into too many details here, but basically you have 2 banks of LED lights, one blue, one green. There are 40 LED lights in each bank of LEDs, so that means each well has its own blue and its own green LED light. So what happens is the blue light will fire, it will go into a specific well, that's across the whole plate, you'll get the response back, it will go through one of the channels, and then the exact same thing will happen through the green channel. And then it will just do that 4 times across the plate, so it will go blue, green, throughout the 4 filter slides. The optical detection in this unit is a CCD chip system, which you can see towards the back there. And there are obvious limitations and advantages of CCD chip technology, which I'll come on to in a second. But as you can see in the top left-hand corner here are the 4 channels over which the system will acquire data. Basically, any dye set between 505 nanometers and 705 nanometers is covered within there. Like I said, there are given advantages and disadvantages to CCD chip technologies. Obviously, one of the main advantages is the speed. The system acquires the entire spectrum in one shot. It's a very cost-effective technology. I'm certain if some of you people are sitting on laptops, you may have a CCD camera staring right back at you at the top of the screen, or on your phones in your pockets or on your desk. There's CCD chip technologies everywhere, so it keeps the cost down for that by comparison to like a photon multiplier tube. And it's a proven technology. But as you get with advantages, you obviously get disadvantages. And the disadvantages of CCD chip technologies are saturation. You can saturate a CCD chip camera or a CCD chip detector very easily, and the dynamic range is very short. By dynamic range, I mean the ability to acquire low light and high light. That would be the dynamic range of the unit, where it fails to acquire any more or where it cannot detect any to start with. So those are disadvantages, but there are general optical considerations as well, which you must bear in mind, and those are crosstalk and saturation. By crosstalk, I mean bleed through from one channel to the next, or saturation, where you just swamp out the detector and you lose all ability to acquire data thereafter. So why would we use a CCD chip detector then? It sounds like I've given you a lot of bad reasons as to why you would use it. And absolutely, those are true of all CCD chip technology. However, the way that this unit works is it actually applies a patented technology called the adaptive LED control. Now, basically what happens in the adaptive LED control is that the amount of light going into every single well on the plate from each of the LED lights is changed such that the response back from the plate is exactly the same. That response back from the plate is such that it is always within the dynamic range of the CCD chip detector. So it sounds a little bit of a strange concept, but it's basically exactly what happens in all other systems. You're measuring the change in light. In most systems, you shine a uniform amount of light to the plate, and then you measure the change back out. All we're doing is changing the amount of light going into the plate such that the response is exactly the same. So we're still measuring change, it's just we do it a little bit before. And by doing that, by using this adaptive LED control, we take out any chance of the detector being below its limit of detection or being above its limit of detection. So there's no chance of saturation. We get a maximum dynamic range that is possible to achieve with this detection system, because for low levels of signal or fluorescence, we simply give a longer exposure time of light, and for a very, very high signal or fluorescence, we drop the amount of light into it. So it's very simple. It's a bit like an auto-expose for every single channel, every single cycle. Like that last point says, an entirely unique feature to the ECO, and one which confers this ability to correctly control qPCR and the ability to detect incredibly low levels as well as very, very high levels. Now hopefully what we should have here is a brief video showing that. Okay, well what that slide was meant to show you was a very brief video just showing you the various fluorescent signals as it goes across the block. That's not that important as long as you roughly understand what I was talking about there with the ALC. In that it's basically an auto-expose for every single channel. That's a fairly complicated system, the ALC, so I'm happy to take questions on that later on if there happen to be any, or go over it later on. The thermal unit, however, this is a very simple system. So basically what we have here is, again, it's another patented technology where what you have is this block that you see in the middle of the screen here is actually a solid silver block. But by solid silver, I mean a very high concentration silver. The block itself is actually hollow. Within the block is actually a thermally conductive fluid called Novec. That thermally conductive fluid transfers heat at ferocious speeds and with great uniformity. Overlying the top of the block is then a protective coating of gold. That's purely there to protect the silver from anodizing, but it's also very good for thermal conductance. So what you have is this block with the fluid is exactly the size of one single Peltier element. Now this is quite important for the next point on this slide where you see the unparalleled uniformity. Because we have one source of heat transferring to a metal which wants to just transfer heat incredibly quickly, that being silver, into a fluid which just wants to transfer heat, and that fluid is in constant motion. What you have at the north and south of the block is actually two little brushless motors, and they have paddles which are inside the block, and they rotate those paddles inside the block, so you get this constant motion. Think of a water bath and think of the uniformity confirmed by a water bath. But what you have here is a water bath which ramps incredibly quickly. We quote a 5.5 degrees per second average ramp rate. Stephen will show you some data later on which exploits this fact. And this 5.5 degrees doesn't sound the most impressive sort of ramp rate, but when you consider that as a ramp rate which has been an average of a change in 100 degrees Celsius, 50 degrees up, then 50 degrees back down, it becomes a very, very impressive statistic. If we were to quote this just as a purely maximum ramp rate, the maximum ramp rate up would be in the 20 degree per second range, and then the way back down would be in the 15 degree per second range. But we quote things in terms of average because it's much easier for people to understand that then a change in 50 degrees should take about 10 seconds, rather than saying, oh, the maximum's 20 degrees, so you would expect it to do it in 2 or 2.5. So we find the average ramp rate far more meaningful. That plus or minus 0.1 degrees is about 5 times better than the industry norm. But actually, the industry norm is to quote thermal uniformity after a period of hold, so maybe after 40 seconds or something, but at a lower temperature as well, at something like 55 degrees. And that's an easier thing to achieve. Our uniformity, which is again something that Stephen will highlight later on, and it's something that we exploit in the system to generate good qPCR data, is defined at 95 degrees Celsius with 0 seconds hold time. So it's 5 times better than any system on the market in a block-based format after 0 seconds at a higher temperature. So it's an incredibly important point to have a thermal unit this uniform. Because, as people are aware, qPCR and PCR in general is driven by heat. Poor control of heat, poor control of PCR. So you need that level of uniformity. If we look at a typical 96 well system, or a system which uses a solid state block, you can see here the two Peltier elements underlying that top picture. So you've got multiple heat sources. And what does that mean? Multiple heat sources just means multiple points of heat. So you've got variation there. And if you look at the heat map in the lower picture, you can actually see the difference in temperature across that block. Now, for you guys that are out there and experienced qPCR users, as I'm sure a great many of you are, you'll be familiar with edge defect, or the fact that you'll sometimes see variation within replicates. That is something that you do not get with, or you limit greatly, with the eco, purely for the fact that it's impossible to establish a heat differential. You cannot establish that because the fluid is in constant motion. So what you get is a more uniform response from your fluid or from your reaction mix, and that just confers more control over your qPCR reaction. So with that, what I'm going to do is I'm going to pass over to Stephen, who's then going to talk us through his work with the system and some of the research he's done in optimizing qPCR runs. So over to you, Stephen.
Thank you very much, Andrew. What I would like to do, really, briefly explain why we use 48-well PCR instruments. We have two, in fact. One is the old Illumina instrument, and one is the new PCRmax. And we have 4 other instruments in the lab. And of course, you use different instruments for different purposes. I'd like to just confirm in our hands how the instrument performs, and then just really discuss some of the applications that we use the instrument for. Essentially, my main use for the PCRmax is assay development. So let's start with the first question. Why would I want to use a 48-well PCR instrument? Well, firstly, of course, it is important that it performs as advertised. And here are 2 experiments we've carried out of 48 wells, different CQs, and essentially, as you can see, the results are virtually identical across the block. In this case, we're using 5 microliter reaction volumes. So in our hands at least, the instrument performs very, very well and as advertised. Now, because the plate is the 384 well format, very small wells, it is possible to use very small volumes of PCR. And this, of course, helps with saving reagents. We're always interested in getting best results for least expenditure. And so a lot of people still use 20, 25 microliters. For most PCRs, that really is not necessary. As you can see in this case, we can get very nice reproducibility down to 1 microliter reactions, and even 0.5 of a microliter has worked here. In general, we would tend to use 5 microliters, and if we want to have maximum reproducibility. So one of the advantages of using a 48 well, or the PCRmax 48 well system, is that it is quite easy to go down to 1 or 0.1 microliter volumes. Just as an aside, we use the BioHit pipettes for all our pipetting, because in my hands these work simply. These are the best ones, the most easy to use ones, and the most accurate ones. So here's just another example of going from 15 microliters all the way down to 1 microliter. And as you can see, in this case, the 1 microliter wasn't as accurate as before, but the 5 microliters consistently gives us very good results. So as I say, that would be our typical volume. The other thing we can do is we use, again, try to minimize expenditure. If we don't have 48 wells to load, we will, example, some of the runs I'll show you later, we only did 4 reactions at a time. So I can use the same plate several times over and save on consumables there. So that's quite easy to do with the ecosystem, because it's not a heat seal system, it's an adhesive-based system, sealing the wells. If you use the same instrument repeater run, you get virtually the same results. So this, of course, is very important when you're developing assays, because you want to be certain that the conditions you're developing are reliable and reproducible. So same instrument gives you same result. So we have 2 instruments, as I say. The first one was acquired in 2012, and the second one we just had a few months now. And essentially, both instruments give exactly the same results. Again, this is nice because it means you can link several experiments, several 48 well plates together, and there's software that allows you to essentially combine the results from multiple plates, and Andrew can tell you more about the technical detail there. But that's a very nice feature of the instrument. So let me move on now to discuss some of the ways that we use the instrument, and some of the ways that might help you improve on your PCRs. Typically, a lot of people still use these conditions. A 3-minute denaturation, which activates the hot start polymerase, followed by anything from 5 to 15 seconds of PCR cycling down to a minute of polymerization. And this is an example of a protocol that a lot of people typically use. And as you can see, this PCR reaction takes around about an hour. Now, an hour is a very long time when you're impatient, like what I is, and want to get on with it. And so there are ways of running faster PCRs. And in our hands, the fastest enzyme that we've come across, and the one we tend to use a lot, is Kappa's master mix. And as you can see, they suggest much faster conditions than the previous one I showed you. And here's an example, I hope you can see this, of a reaction mix run for a very short period of time. In fact, we're halving the denaturation and the polymerization times. And as you can see, we're down to a 34-minute reaction time now. However, we can go on and reduce that even further. And we can now reduce the polymerization time to 5 seconds and essentially get the same result. And we can reduce to a 1 second and still get essentially the same result, as shown by the graph here. So 10 seconds, 5 seconds, and 1 second annealing stroke polymerization times with the Kappa enzyme give you the same result. and we've now managed to go from 1 hour PCR down to a PCR that takes less than half an hour. But we can, really this depends very much on the master mix you use. It doesn't work for every master mix. So you have 4 different master mixes, and as you can see, reducing the polymerization time from 5 to 1 second gives you somewhat less good results for these 4 master mixes. And all I can emphasize is that when you're doing experiments, it's always worth your while testing out a range of different master mixes because they do behave quite differently. And having said that, of course, a master mix that is optimal for speed may not be optimal for multiplexing. So again, that's why there are so many different master mixes, because they do perform differently. Now, the other thing that people tend to overdo is the denaturation times, and there really is no need to denature the reaction for 15 seconds or even longer. Here we have a 5-second denaturation and a 1-second denaturation. And A, in fact, is a kappa enzyme. As you can see, it makes no difference whatsoever for kappa, whether you denature it for 1 second or for 5 seconds. Other enzymes like B and C here does make a difference. So again, if you use the right combination of instrument and master mix, you can in fact reduce your PCR times quite considerably. The other thing, of course, a lot of enzymes need to be denatured to activate the hot start for 3 minutes or even 10 minutes for some. This is the kappa enzyme, which after 3 seconds gives the same result as it does essentially if you leave it for 3 minutes. And so these are just a number of steps that you can take to reduce the time it takes to do PCR. And as you can see, we're now ending up with a 3-second activation, a 1-second denaturation. And in fact, you can see I've denatured at 90 degrees rather than 95, and a 1-second polymerization, which we can now do in 16 minutes on the ECO. So 16 minutes is just about enough time to pour a cup of coffee, not to drink it, which is slightly inconvenient. But nevertheless, the point I'm trying to make is that we've gone from an hour to less than 20 minutes to run an assay, which is can be very useful if you've got lots of assays to assess. It depends, of course, on which on your assay. Some assays do work better than others, obviously, and the key to a good assay is having as short an amplicon as possible. Typically, our PCR amplicons are somewhere between 60 and 80 nucleotides. And you can see here we typically have 2 results. These are very similar conditions. The main difference is that, in fact, on the right you can see we've gone down to an 88-degree denaturation temperature now, and that has reduced the whole assay, including a melt curve analysis, to 18 minutes. And you can see the melt curves are very similar and makes very little difference. So one of the nice things about the instrument is the melt curve speed, which takes just a couple of minutes essentially. On some instruments it can take half an hour to do a melt curve. Denaturation temperature is important. Most people use 95, but as you can see, these are different master mixes. Down to below roughly around 86 degrees, the enzymes perform more or less the same. So you can go down to 86 degrees, and some enzymes, in fact the black one is Sigma's Kickstart, you can go down to around about 82 degrees. This is important because the instruments, any PCR instrument takes longest to cool rather than to heat. So the 95 to polymerization temperature is the longest step. So if you can minimize the temperature difference between denaturation and polymerization, you can speed up the assay significantly. Of course, you have to have the right master mix. Now, you don't have to have a fast master mix a more expensive master mix to do a fast PCR. Here's a conventional master mix, which is Bio-Rad's IQ, which is a very nice, very old master mix. But as you can see, if you follow their instructions, the recommended conditions, the assay takes an hour, 59 minutes and 20 seconds to perform. However, if you reduce both the denaturation and polymerization times to 5 seconds and 15 seconds, again we've gone down to 34 minutes of PCR. and so on. We can reduce it even further. It's only when we start going down to a 1 second and a 5 second polymerization time that the CQs now have gone up from 15 to 19. So this enzyme can't cope with a 5 second polymerization time, but it copes with a 15 second polymerization time. And instead of the recommended 60 minutes, we have 31-minute PCR. So it is always worth your while, if you're considering speeding up your assays, playing around with whatever master mix you're already using, because the conditions that have been given to you by the manufacturers are very generous, and there's a lot of leeway to improve or to speed up the reaction. This simply shows you, again, how reproducible the ECO is. Here we have 8 replicas of 3 different primer sets for different targets. And as you can see, our standard deviations are very, very low. And the delta CQ for all these 8 replicas is around about 0.2. And in fact, I wasn't even trying to do any particularly accurate pipetting here. And these are all done in 5 microliters. Now, a lot of you will be interested in multiplexing, and just a few pieces of information here. Master mixes tend to be important when you're multiplexing. So what we have here is 2 different master mixes and different probe concentrations. As you can see, the master mix at the top gives you a different result depending on which concentration. If you double the probe concentration, you get a better result essentially. Whereas the master mix at the bottom, it doesn't really matter what you do; you get essentially the same result. So some master mixes are much more robust for multiplexing. Again, if you are doing a multiplex reaction, it's well worth checking a few different master mixes, and not necessarily the ones that are advertised as optimal for multiplexing. In our hands, one of the ones that works really well is Quanta's master mix. And the other thing to remember is that some master mixes just don't perform well at all. Here you can see a 4-plex. As you can see at the top, you get a nice result. All 4 amplicons give you nicely distinguishable amplification plots with clearly different CQs. At the bottom, a different master mix, and whilst amplicon 1 and 2 are more or less the same, 3 and 4 now aren't really distinguishable. They give you essentially the same result. Which one is correct? Well, I don't know, but clearly they are different. So bear in mind that if you have a problem with your multiplexing, it is worth playing around with the experimental conditions, probe concentrations, primer concentrations, or even magnesium concentrations. But you may well need to switch to a different master mix, and suddenly you get a very nice result. And the only difference is the master mix, not the assay you have designed. The other thing to bear in mind is that if you order a new probe for a reaction that's worked nicely, it may not necessarily work again. Here's an example of using the old probes which give you, in a multiplex reaction, it's a triplex reaction here, nicely 3 different amplification plots, whereas the new probes are all over the place. So it's always well worth your while ordering before you run out of the old probe, because the new probes mightn't perform to the same standard. Now here's something else I'd like to discuss with you very briefly, and that is the problem of master mixes. The results that you get can be master mix dependent, and you might think that we know all we have to know about PCR, and that, as we know, PCR is very reproducible. This is all true, and if you do 10 replicates of a PCR, you'll get essentially the same result for each master mix, but you can get different results for different master mixes, even though within each master mix you get the identical result. So here's a very simple experiment, a cDNA reverse transcribed, and then pre-PCR mixes that contains everything except for the master mix, and then that's added to 5 different master mixes. And here are the results. Just a quick glance tells you that they are similar, the results are similar, nothing obviously different about these. But if we now do what most people do, relative quantification against, in this case, what is recommended, 3 reference genes, then for MMP3, is the first target, you can see that the fold changes are very much master mix dependent. So, in fact, the difference between the master mix A and master mix C is a 12-fold difference. So the only difference here is that we've used 5 different master mixes. And this is something I've been saying for a long time. We have to be very careful when we discuss fold changes in qPCR, because a lot of people report 2, 3, 4 fold, 5 fold changes, and sometimes this can be simply due to the fact that they're using a different master mix, or in fact we already know that the RT step is highly variable. Here's a second example for IGF-1 receptor, where we get an 8-fold difference simply based on the master mix. And this is very much marker dependent. So here we have from COX-2, which gives you essentially the same result for each master mix. And on the other extreme, we have COX-1, which is a 25-fold difference. So bear in mind that the result you do get can be master mix dependent, and that makes it so very difficult to know when you're reading papers and you have discordant results being reported, which is the one to believe. And of course, that is one of the reasons we have the MICI guidelines that then gives you the information that you need to be able to reproduce and assess published data. A typical PCR setup looks like this: 20 microliters or even 50 microliters, and again, oops, what happened there? Now, you see that these results are very, very similar for both Bio-Rad's IQ and Sigma's Jumpstart, but in fact, what we've done here is, rather than adding 1 volume of master mix to 1 volume of target, I've reduced the amount of master mix I'm adding. I've gone from 1 times master mix, which is the recommended amount, down to 0.7 times master mix, essentially saving 30% of the master mix in that reaction. And as you can see, the CQs really don't change different very much. So again, a good economy tip is you don't need to use master mix that is at 2 times concentration at 2 times concentration. You can actually use far less than is recommended. And it may not work for every master mix, but I've looked at 14 different ones, and it has worked for all of those. So you don't need to use 1 times. Use 0.7 times or 0.8 times if you're not happy, if you don't believe me. But try it yourself, and you'll see you get the same result. Now, finally, I'd like to show you a problem with master mixes. As I say, we have been dealing with PCR for a long time, and most people are convinced or think it is a reliable and reproducible system, but there are still lots and lots of problems associated with technique. And one of the ones is one of the reagents, which is the polymerase itself. Now, you may remember a long time ago that there were no hot start enzymes, and very soon, this was in 1991, yes? So a few years after PCR was first published, it became clear that there was a problem with carrying out a PCR where you assemble all your reagents at room temperature or even on ice, because the primers will bind to the target and the polymerase will start non-specific polymerization, which, if the conditions are right, can give you amplicons that are non-specific. So this led to the development of hot start polymerases back in 1994. And I think most people these days would use a hot start polymerase for their PCR reactions. Now, I'm not sure how companies assess the quality of their hot start inactivation, but this is an assay that was published for different purpose altogether. It's used by a British company at the moment, Momentum Bioscience, to look for polymerases from pathogens. But I've adapted it to look at the polymerization efficiencies of commercial polymerases. And essentially you have 2 oligonucleotides that have partial overlap, and oligonucleotide 2 has all the T's replaced with U's, and it's blocked at the 3' end. So, as you can see, they can anneal like this. And if you add bacterial lysate to this, if there is an active polymerase present, that polymerase will extend across the oligo 2, and you end up with 2 strands. One contains a full DNA strand, and the other contains U's. If you add uracil N-glycosylase, the second strand is degraded, and now you have an amplicon that you can amplify with a reverse primer, carry out a PCR reaction, and if there was a pathogen present, you get a result. If there was no pathogen present, then because the UNG has destroyed the second template, there will be no CQs. So a very simple assay that allows me to test the quality of the hot start activation. So what I do is very simple. I have a premix, contains templates, DNTPs, and my TAC buffer, to which I add some master mix. And rather than adding 1-to-1, I add 1 microliter, 1 volume to 10 volumes of template. So there's very little of the master mix present. And I incubate these at different temperatures. So at the bottom you have a 95-degree activation step followed by a 25-degree incubation for 30 minutes. Then the second condition is leaving out the incubation step at 95 degrees, so there's no activation, but still continuing the incubation at 25 degrees for 30 minutes, and then simply leaving the reaction on ice for different periods of time. After that, I treat with UNG, and I use ABI's fast mix, which happens to also contain some UNG, so there's a second UNG step there, but then do a standard PCR reaction on this. And these are results for 3 different master mixes. They're slightly different, but then we expect them for different master mixes. But essentially we're getting the same result. 3 master mixes that have been activated and allowed to polymerize give us CQs around about 25, and the negative control is negative. If we do the same reaction except leaving out the 95-degree activation, this is the result we get. All 3 master mixes give a result. Master mix B kind of doesn't. Only one of the 3 replicates gives a result, but nevertheless there's something there. Negative control is again negative, but look at A and B, A and C. All 3 replicates, and in fact A gives you very much the same result you got even with the activation. So A is not terribly well inactivated, and neither is C. And here are the results for the different lengths of time that the reaction has been incubated on ice. And as you can see, for master mix A, you get a result in every case. For master mix B, kind of, clearly it is inactivated. Not 100%, but it is inactivated. And C is variable. Negative control is negative in every case. So this suggests that at least for 3 of these master mixes, for 2 of them, there is a problem with the hot start inactivation. And that's what it looks like if you plot the CQs against the different treatments. And so if you repeat this protocol, everything exactly the same, but this time, rather than leaving it in ice for 3 hours, I've left it in ice for 48 hours, just to simulate the fact that what you might do is pre-prepare your plates and then use an automated robot to mount your plates and do a PCR reaction. So that's the only difference here. And here are the results, comparing the 2 experiments. So very much the same result for experiment for the activated polymerases. It's a very similar result again for the inactivated and the one that's been left in ice for an hour. And now if you compare the 48 hours and the 4 hours, you can see after 48 hours in every single instance, even for enzyme B that has given us less activity, there's significant polymerization taking place. So what this means is that despite the enzymes being hot start enzymes, if you leave your reaction mix in the presence of polymerase, you will get some nibbling or polymerization of the end of your target. And because, of course, you are way below your optimal annealing temperature, you'll get a very non-specific reaction that can affect the sensitivity of your assay because you will have non-specific targets. And in the worst possible scenario, by chance, you may get a new amplicon that can be amplified by PCR. So in summary then, I find the PCR an ideal instrument for my assay development because it has very good performance, it is very cheap to run, and it is very fast. So I can get lots and lots of different runs on, and because I can run 2 instruments at the same time and compare the results easily across the 2 instruments, it is a very efficient way of developing assays. When you're looking at master mixes, bear in mind that they can differ considerably in their performance. So if you want to have speed, you'd use kappa. If you want to use optimum denaturation temperature, you might want to use sigma's kickstart. And if you want to use a multiplex reaction, you might want to use a different master mix again. So it's always worth adjusting or tailoring your master mix to your what you're trying to do. But bear in mind that different master mixes can give you different results. And particularly bear in mind that some are better than others in terms of hot start inactivation. And finally, it is quite easy to reduce your costs because you can, rather than using 15 or 20 microliters, use 5 microliters, and there's no need to use your master mix at a 1-to-1 ratio with your template. You can go down to 0.7 times and still get a good result. And you can reuse the plates quite easily by simply cutting off the seal and resealing it with your fresh reaction. And I think that is all I have to say, and I'll pass you on to Andrew now again.
Okay, yep, thanks Stephen for that. Yeah, so just to follow on from Stephen very briefly, we have one other slide which is basically just a quick summation of what we've covered so far. So with this unit and with using correctly optimized conditions, and as Stephen's highlighted, not all TAC is created uniform, and certainly immobilization might be something that you have to look at for specific things, but certainly with this unit, given the uniformity, given the reproducibility that you can get at those speeds as well, you can really foreshorten run times with this unit. And remember, like I said right at the beginning, every single read that this system's taken, it's still acquiring data from the entire plate using all 4 filter slides. So even if you'd set up the conditions wrong with using the filter slides or whatnot, or you thought you had used a different probe set, hopefully you wouldn't do that, but the data is still there, it's still captured there. It's an open platform. Stephen's, well, very competently demonstrated that. There's no limitation to this system as to which chemistry you can use. You can use literally anything you want on it. And there's quite a lot of publications out there to back up this system, including a few which actually directly compare this technology versus other technologies. But one thing I would like to mention there as well is one of the slides that Stephen put up earlier is about that comparison between the 2 units, where you have an older unit compared to a new unit. And that's something that actually, it's a testament to the uniformity and what that actually means. Well, what it means is that you can have prolonged service of this unit, and certainly the units that Stephen have they're not wrapped in bubble wrap and put in the corner and not used. They're well used daily, and Stephen's still getting the same results from a unit which is 4 years worth of use versus a unit which is basically within the last couple of months. And that just again is testifies to the accuracy of that block. But what Stephen mentioned is that the software allows you to exploit that capability. And it allows you to combine multiple runs together and analyze that as one data set. So it allows you to massively expand upon the amount of work you can do. That goes hand in glove with the total reaction volume, so you can do more with what you've actually already extracted. And that's key and very important in qPCR, as I've found. So with that, that's us down to the end of the presentation section to this slide deck. So what we'll do is open up to some questions now. So,
thanks, Andrew, and thank you, viewers, for joining us for this part of the webinar. Now we are going to, as Andrew just said, start with some questions for our experts. And of course, we have a few questions about the master mix. So, Stephen, could you walk us through this question? How do you overcome master mix to master mix variation? And have you observed variations in different lots of the same master mix?
Yes, well, yes, there can be differences. It depends on the manufacturer. Some master mixes are much better than others. So if you buy a master mix from a good manufacturer, then there will be no variation even between different lots, or very little variation. The important thing to do is, what I always do and always have recommended, is running standard curves, because when you have standard curves, then you can relate your results directly to the standard curve on the day. And then that will minimize variations you have from your master mix. That would be my advice for that.
Okay, great. Thank you. Let's see, and we have another master mix question here. For master mix A, B, and C, when you are testing the hot start functionality, where A, B, and C antibody or conformational change immobilized, Did they have an antibody bound to the active site or need a conformational change to be active?
Yes, they were active site antibody. I haven't actually done a complete comparison of all the different methods that that companies use, but we're hoping to publish this, so that will be part of the publication, I think.
Okay, great. Thank you. We have a question here. At the beginning, Stephen, you mentioned the 48 well plate can be reused. Do you have to wash that? Could you maybe expand on what you were speaking about?
No. Okay, so what you do is, let's say you've run 16 reactions. The first two rows have been filled. So what I do is I cut off the seal from the remaining wells. Obviously leave the wells that have been subjected to PCR covered, and then simply refill whatever many wells I want to use and reseal it, and then run that plate. And the maximum I've done is eight different reactions on the same plate. The important thing to do is to never expose the wells that have been subject to a reaction, so you never lift the seal off those.
Okay, thank you. Here's another question for you, Stephen. Have you found a threshold of reaction time based on your real-time PCR amplicon length? For example, amplicon greater than 100 or 120 BP cannot be used?
Yeah, well, firstly, let me say that we don't use anything that's really longer than 80 in general. But we have used some longer amplicons, and they still work. Kappa is, it certainly works with Kappa enzyme. Now, I think the speed of enzymes is vastly underestimated. I'm sure many of you will know Carl Witwer, who invented the light cycler, and he has a nice video where he carries out a 40 or 35 cycle PCR reaction in 17 seconds. So I'm not quite sure how long his amplicon is, but I know it's certainly longer than 100 base pairs. So I would be confident that even a longer amplicon can be amplified very, very fast.
Okay, thank you. Going back to a different part of your presentation, when you were talking about comparison of instruments, the comparison that you conducted, was it done on the instruments? Was the comparison of the instruments purchased in 2012 and 2016 undertaken at the same time, or when both instruments were first purchased?
Yes, they were done last week or 2 weeks ago, so they're done now. So the old instrument, its performance has not deteriorated in the 4 years we have used it. And I must say, we use the instrument every day, all the time, so it gets constant use. And it's never been serviced or anything, so it's been extremely reliable.
Thank you, Stephen. We have time for maybe 2 more questions. We'll throw one to Stephen and one to Andrew after that. Last one for you, Stephen. What reaction volume do you routinely hand pipette and run in the lab?
Routinely, we pipette a reaction volume of 5 microliter reactions would be our standard reaction. If I really want to be cheapskating, I would go down to 1 microliter, and we use the BioHit M3, which allows you to pipette down to 0.3 microliters. But we do then, I think you saw it in one of the slides, you get more variability. So unless there's a really good reason to use less, we would use 5 microliters.
Great, thank you, Stephen. And Andrew, we're going to throw one more to you to wrap it up. We have just a minute or 2 left. So could you quickly go over the ALC technology again for the readers?
Sure, no problem. Yeah, the ALC technology, it's a fairly tricky sort of concept to get your mind round initially, but all the system's doing is exactly what all systems do, and it's measuring the change in light. Simply, all we're doing is changing the amount of excitation light going into the plate such that the response from the entire plate, irrespective of how great or how little the fluorescence, the amount of DNA is in there, that it's exactly uniform. The easiest way to think about it is it's a bit like an auto expose for every single channel, such that the response is always perfect amount of light for your detection system. The advantages of it really are that you will never saturate that detector. So everyone's measuring these lovely things called unknowns, where sometimes you just don't know where the upper limit's going to be. So the fact that you have this adaptive control where it can basically like attenuate down the light such that you never run into threshold problems of being above or below the detection system is why the ALC is there. So it's basically an auto-expose such that you take out any limitation of an optical unit.
Perfect. Thank you, Andrew. In the audience, that's about all the time we have today. So I just want to say thank you to you guys for joining us. Thank you to Stephen and Andrew for their wonderful expertise. And thank you to Cole-Parmer for sponsoring this event. Audience, we hope you found it informative and educational. The webinar has been recorded for your convenience, so it'll be available on demand within 24 hours. And we hope to see you soon. Thank you so much.